All right. Hi, everyone. I'm Mike. I'm very happy to be here. I don't do a lot of very high redshift stuff, so it's been very fun being here and being educated by all of you. But I'll have a few things to say about what I think might happen at high redshift regarding star formation and the IMF that may be interesting for some of the things we've been discussing. So let's talk about the IMF. So as was mentioned earlier in this meeting, the IMF is sort of the bedrock on which we build all of our modeling of stellar populations. I'm not sure any of the observations discussed in this meeting yet were actually of individual stars. They were of stellar populations, and we were measuring light. So if you want to get the light, you have to involve the IMF with the star formation history, with dust attenuation and completeness and other sorts of effects. So you need the IMF in order to interpret the stellar populations you're looking at. Now this is a diagram of a whole bunch of different IMF measurements. So what we're looking at is the slope of the IMF in various mass ranges of stellar mass indicated by the horizontal bars. You can get this compilation at the link below. We would really like to understand whether the IMF is universal. That would be great, of course, or whether it could vary from one place to another. It's been noted that the peak of the IMF, where this slope passes through zero, that it has relatively little variation where it's been measured in the local group. But for our purposes, who cares about that? We're looking at light that is coming from giants that are more massive if we're looking at high redshift observations, or just recently formed massive stars of its high redshift. So regarding the massive stars, you have this high mass slope, the salpeter slope. And I would like to point out that actually very little is known about what this high mass cutoff should actually be in general. We typically just assume some maximum mass comparable to the maximum masses observed in the local group. But this is highly uncertain. I'd also like to point out that there are points on this diagram that are confidently top-heavy compared to the salpeter IMF. And these are found in the most extreme regions of the local group, so 30 Doradus and the galactic center, where densities are very high. And by the end of the talk, you'll hopefully agree that maybe this is not a coincidence. So how do you get an IMF? Well, you can start with the simplest possible premise, which is just isothermal gas and gravity, and you just let it be turbulent and collapse under gravity and see what mass spectrum of fragments you get. It turns out you don't get any mass spectrum at all. None of these studies were able to obtain numerical convergence under this set of assumptions. You just get more and more fragmentation as you turn up the resolution. So what saves you here is the opacity limit, which is a classic idea. Basically, this gas is collapsing. It's radiating away its energy via dust emission. But that dust emission stops working once the radiative diffusion time becomes longer than the free fall time. And then your Jeans mass, which was initially dropping as the -1/2 power of the density, will start to rise. So this will set a sort of minimum mass, which sets some sort of low mass cutoff on the IMF. And depending on your ambient radiation field, you can get something that is very insensitive to dust opacity or equivalently metallicity. But if you crank up the radiation field, then you start to be more affected by the dust abundance or metallicity. Some colleagues of mine have shown with some very nice simulation works with the Ramsey's code that if you just put in this opacity limit into your equation of state and you see what mass spectrum you actually get a rather nice looking IMF that agrees with the observed one quite well. I wanted to see if I could reproduce this with my simulation setup with the Gizmo MHD code. So I ran a similar set of equations of state, and I too found that depending on my equation of state, I would get the IMF peak basically wherever I put this minimum Jeans mass due to the opacity limit, and it's also quite insensitive to the temperature at lower densities. So that's great. The IMF is solved, but this is actually a really dense clump. So this is actually much denser than any cloud-forming stars in the solar neighborhood. If we simulate those conditions, then we get this sort of flat, kind of top-heavy looking thing that doesn't look at all like the observed IMF. So I still found that the opacity limit does affect the low mass cutoff that we get here, but we have all this high mass crap that we just need to get rid of if we want to match the IMF. So what are we missing? Well, we're missing feedback. So stellar feedback, in addition to regulating the properties of star formation and star clusters in galaxies, regulates the gas flows that feed individual stars. So you have protostellar jets, winds, radiation, and supernovae. So my collaboration, the StarForge collaboration, implemented the first numerical framework for performing radiation MHD simulations of star formation following the formation of individual stars while accounting for all of these different stellar feedback mechanisms acting in concert, while also accounting for the various other processes that you really need in order to get star formation right. So just to give you an idea of the processes we're modeling here, this is a movie of our first simulation we ran with this setup. So we have a 10 parsec cloud with 20,000 solar masses in it. Dimensions broadly matching solar neighborhood GMCs. So we give it some initial turbulence, we let it go. It collapses in a sort of filamentary, turbulent manner. You get these dense pockets that go on to form individual stars. And as these individual stars accrete, they shoot out feedback in the form of protostellar outflows. And this is playing actually a pretty important role in regulating the gas flows that will feed these stars in the future and their eventual mass that they will attain. And some stars get luckier than others, and they become massive and start sweeping out H2 regions and wind bubbles. So more and more stars will form. The amount of feedback at work is ever increasing. We're color coding by velocity dispersion here, so yellower is more velocity dispersion. And eventually we reach a point where we have so much feedback that we start reversing the collapse of the cloud. We start having less and less dense gas, so there's less and less star formation happening. Star formation is winding down. And at around the 10 million year mark, we actually get our first supernova, and that puts the final nail in the coffin of star formation in this particular cloud. So this is what we do at StarForge. We fire off these gas clouds and see what stellar population comes out while trying to account for all of the physics. So our IMF story so far is as follows. If you just have isothermal gas and magnetic fields, similar to what I showed you before, you get this sort of top-heavy thing, doesn't really work. Doing a more detailed job of the cooling and chemistry gets you more or less the same thing. As soon as we switch on protostellar jets, we start getting something that looks a lot more sensible in terms of the location of the turnover of the IMF from the salpeter part and the actual slope of the salpeter part, but the jets can't really regulate the high mass end, so we still got 400 solar mass star in a solar neighborhood GMC, which if that could happen, we'd have discovered it by now. But when we account for all of the different feedback physics, then we start getting a more reasonable high mass end of the IMF. So what's going on here is that protostellar jets are regulating the IMF turnover and to some degree the slope of the IMF. As I mentioned before, dust radiative processes like the opacity limit will set the low mass cutoff. You have to actually resolve that mass scale, which is it's not in these data here. And radiation and winds from massive stars will regulate the high mass tail of the IMF. So I became interested in that high mass tail. And in this paper, I was able to show that the high mass tail, when I simulated 100 low mass clouds, was very tightly constrained. It was not just a size of sample effect. So there's a cutoff here. It's set by feedback physics because the one cloud without feedback formed more massive stars. And it depends on cloud properties such as mass, surface density, and metallicity. And the reason for that is not too hard to see. So you can do a sort of back of the envelope thing where you ask how much feedback of a certain type do I need to disrupt a clump of a certain mass and surface density within one freefall time. And whether you're talking about momentum feedback or energy feedback or ionizing feedback, you always find that the amount of feedback you need scales as some positive power of the mass and the surface density of the clump. Thank you. So denser and more massive clouds can tolerate more massive stars without being disrupted. As we go to lower metallicity, we also have an interesting effect with dust radiation pressure. So very massive stars are basically at the Eddington limit at the Thomson opacity, but the gas around the accreting massive star is subject to the dust opacity. So your Eddington ratio, the ratio of radiative to gravitational acceleration, actually ends up being just a function of this sort of scaled dust metallicity, or the dust-to-gas ratio. What this means is that at solar metallicity, radiation pressure on dust grains is important, but at low metallicity, radiation pressure on dust grains can actually do very little to regulate the accretion of massive stars. So let's go to the high densities and low metallicities we've been talking about at this meeting. So we fired off a run with these parameters, 100 times higher surface density, 100 times lower metallicity, and this time we actually got a maximum stellar mass of about 1,800 and 3 other stars of about 1,000 solar masses. And these stars eventually disrupt the entire cloud with a powerful 100 kilometer per second stellar wind-driven outflow. So that's the velocity of the cloud being dispersed, not the wind itself, mind you. We get a fairly top-heavy IMF, both in terms of the high mass slope, even just ignoring the fact that we have 4 very massive, roughly 1,000 solar mass stars up here, which have half the mass in this whole cluster. So you get a huge UV light-to-mass ratio. You know, these very massive stars might participate in nitrogen enrichment or other interesting abundance patterns. When they die, they're going to be, 1,000 solar mass black holes. So there may well be interesting implications for various problems people here are working on. So just looking at the mass reservoirs these stars feed from, so this is all of the gas in the cloud. This is the gas that ended up in Paul, the most massive star. This is the gas that ended up in John, the second most massive, and George and Ringo. So these stars are basically feeding from a reservoir that permeates the entire cloud. And if we look at a movie of how these stars feed, then we see that, again, the gas that feeds the individual stars, shown in each respective panel, extends out to large radii, and the stars just accrete more and more, and eventually they actually pair up and they start accreting from a common gas reservoir. So if we look at the accretion rate, then we find that the accretion of these 4 very massive stars is highly correlated. And if we take out the dominant scaling, it looks like an m to the 2/3 scaling in the mass accretion rate, which is consistent with this picture of competitive accretion where the cross-section for a star to accrete gas is limited by the size of its Hill sphere in a tidal field. So this highlights an important point, which is that very massive stars are forming at low metallicity, not due to a higher Jeans mass due to the thermal processes, but due to this runaway accretion. And I'll skip that slide and just leave you with a picture of what I think the anatomy of the IMF might look like based upon a large body of work. So you have your low mass cutoff due to dust radiative processes. You have this turnover, which is sensitive to turbulent fragmentation, but also, as we saw, protostellar outflows. You have this high mass slope, which may also be due to turbulent fragmentation, but as we saw in Starforge, it's more of a runaway accretion type effect. And you have this high mass cutoff, which is set by feedback from massive stars. And as we've seen, this high mass cutoff could get very big at high surface densities and low metallicities, and this may prove important for high redshift galaxies. Thank you.
Rafaela, can we get some help again? Just wait for the mic for a moment.
I have a question on, comparison between your simulation results for present-day star-forming conditions. So have you tried to see if you can actually fit, for instance, observations of the core mass function? Because the core mass function, which is, preceding phase with respect to the final, IMF, can give you a handle of exactly this interplay between feedback and fragmentation and accretion.
Yeah, no, we haven't really done much with the CMF. I would like to do that. I would like to do that right, which means doing mock observations and measuring it the same way the observers measure it. But you're absolutely right that that is a very interesting diagnostic, and maybe the simulation is getting that completely wrong, and that can help us narrow things down. So I agree that that would be valuable work.
Marta?
Thank you. I have two questions. Hopefully they're short. So the first one is on your comparison when you showed the mass function of your work with Patrick and Nebel's. You said that if you were using solar neighborhood conditions, you were getting a mass function that was totally wrong. So in Patrick's work, did he use these extreme exactly, the extreme densities or solar neighborhoods? So can you give more details on the comparison between your work and this?
Yeah, so both of these works considered only these extreme densities. And I think it's actually quite likely that they would find the same thing as I do if they simulated similar conditions.
Okay. And the second is about the last part of your talk. You were showing stars with masses about 1,000 solar masses. This was with solar metallicity of 0.01 solar or something lower?
1% solar.
Okay. So in that case, I would expect that the mass of the remnant black holes will be a very small fraction of the stellar mass and not, very massive black holes just because of the opacity.
So you're asking about the relation between the zero-age mass and the eventual remnant mass?
Exactly. So if you are at 0.01 solar, I would expect that the final mass of the black hole at the explosion of the star would be a few tens of solar masses at most, and not a significant mass of the initial mass of the star. I just wanted to check if this is also what you were expecting, or you were expecting a more massive remnant.
My impression here is that the mass loss of such massive and metal poor stars is actually kind of uncertain. So I think there's parameters, there are convincing models from people who do this that would predict that these stars would not actually lose a large fraction of their mass over their lifetime, but there are also models that seem just as physically convincing that would predict that the stars would lose a very large fraction. And the truth is we don't really know because we don't have observations of such massive stars. But that's been my impression of the sort of model space of mass loss.
Rachel?
Thanks a lot, Mike, for a great talk. So I'm wondering about something that you may not have really looked into, and if that's the case, that's fine. And that is basically the interplay between these massive stars, sort of what's sometimes called early stellar feedback processes, and the supernovae, right? So if the densities in high redshift galaxies are very high, as we've been hearing, 10 to the 4 or above, then of course the freefall times and the disruption times of these clouds or clusters are very short. So presumably the supernovae are exploding in relatively low density gas. But I guess I just wondered if you've actually looked into this in those kinds of environments and those kinds of settings, and do you have any comments at all about how you think supernova feedback might be different in these high density environments?
Yeah, and I think environment is the key word there. So we only run these very high density runs for a few hundreds of thousands of years. So then you've got the whole main sequence lifetime of the massive stars ahead of you. And what environment those supernovae go off in 40 million years later is going to depend on what happens, many, many dynamical times after we've finished the simulation and the gas is dispersed. So yeah, you'd have to put that in a galaxy simulation and see what happens there, and hope your galaxy simulation is actually resolving the relevant processes. Yeah.
Nick?
So sorry, it's a great talk, and sorry for question. Maybe it's very uninformed. Just the context that I'm kind of missing here. In 2012, 2013, Phil Hopkins wrote a whole series of papers when he used pressure actor for formalisms that cosmologists understand, and he was actually derived, analytically, essentially, as mass functions IMFs, right? Or it was actually mass functions of course, not exactly IMFs. And he had all these properties without all this physics that you talk about. And so I'm just really confused how your model and how Phil's model, how they mesh together, if at all. So can you give maybe like a bigger context of here?
Yeah. Phil's model assumed the same thing I sort of started with at the beginning of the talk, which is just gravity plus turbulent isothermal gas. And when we went and simulated that, we got no IMF whatsoever. So that could be an issue of mapping Phil's core mass function to the actual IMF, because there's a lot of processes that occur going from one to the other.
Presumably you can have a star which is more massive than the core from which it forms.
Yeah, exactly. Like I showed you.
The function limits is an envelope around and it has the same shape.
Yeah.
So you can just have a power IMF under this core mass function because it already limits you at all times.
Yeah. As I also showed, these very massive stars, they're accreting from very extended reservoirs that go far beyond the initial core that seeded the initial collapse of the protostar. So I would say that is a distinct picture from the picture of the high mass slope in Phil's model as well. So I would say Phil's model is in some tension with what happens in the simulations, and I think I would have Phil's blessing in saying that.
Okay, and the last question, and if the next person.
Thanks for a great talk.
Forward.
So I'm used to galaxy formation simulations where the stellar
Can the next
feedback
speaker already
modeling.
come forward?
I'm used to galaxy formation simulations where the stellar feedback modeling has a bunch of free parameters. But here you have like much smaller scale simulations with much more ab initio, so to speak, modeling of stellar feedback. So I was wondering, there's two questions I have. The first is, are there any free parameters in your feedback models in StarForge? And I forgot the second question. But oh yes, so yes, can you use your StarForge simulations to predict as outputs what goes into as inputs in the galaxy formation stellar feedback modeling?
Yeah, great questions. So